We've got, I think, 30 minutes to go over code coverage and then jump into this wondrous world of continuous integration. We'll do walk through a repository and a live demo if all things go well. So there was a previous member of this tutorial team named Alicia Klinvex who used to give this part of the tutorial originally. So a lot of the slides that I'm going to be showing here are originally from her. So code coverage. The idea is that we've done a lot of work in writing some code. We've also been very good, and we've packaged that up with a nice set of automated tests, and we want to try to get some idea of how good of a job we've done in setting those tests. Just because I've got those tests running and they all passed, does that mean that I don't have any bugs in my software? That's what we're essentially trying to get at with code coverage, right? And so one of the things that we can do is use a tool like gcov and look at code coverage by line. So we'll be able to build our test suite in a certain way, run it, and immediately get a number. 80% of the lines of your code are actually being executed by your test suite, right? And so that's what we're going to do. And what we also like about this code coverage analysis is that it can help us, when we're not at 100%, identify where are the gaps in our test suite. And that can also be helpful. So if, for instance, we find out that we have, let's say, 5 gaps, we can try to figure out which is the most urgent one to get covered, to get under coverage by our test. So we can look and find, OK, this one particular gap, I'm not covering this particularly nasty part of the code that's really hard to write. Or maybe it could be that people are oftentimes tweaking the code in there. And so it makes me a little bit uncomfortable that I don't have some tests to check that. And so I'll put my upfront effort, therefore, in getting that part of the code under coverage. So this tool gcov, it's a standard utility with the GNU compiler collection suite. The way you use it is when you want to build and run your test suite, you compile it and link it with this extra flag -- coverage. And they suggest that you turn off optimization so that the results that you get are more in line with what you've actually written. And what it's going to do when you run the test suite is under the hood, it's going to be counting the number of times that each statement has been executed, and it will create some intermediate files, and then you can use gcov itself to run on those intermediate files and extract the results that you're looking at in terms of the % code coverage by line, as well as you can look and see which lines have been called how many times. And so if you're not a fan of the ASCII format files, there's this lcov tool, which is a graphical front end, and it will create some very basic but nice visual output of that particular code coverage analysis. And nowadays, there's also these hosted servers, which are Coveralls and CodeCov, I believe, and they have some pretty swanky graphical visualizations and some nice way to look at the analysis in a different way. And as we'll see later on, if you use one of these hosted servers and you're using a continuous integration test server, you can also connect those two together so that you can trigger some code coverage analysis and immediately get it into that host. So this is what one of those hosted server outputs look like. So I created this little toy repository on GitHub, and I put in this nice file modulo mod.f90. And I have a test suite associated with all the code in there. And when I run that test suite with code coverage, all 3 lines are actually covered. So I'm pretty happy with that. And then I've got this linear function class.f90. And when I run that, only 61 out of 82 lines of code are covered. I'm not doing such a great job there. Not too bad, but not great. And when I click on the link, which is the file name, it'll take me to the actual source code, where it shades in green the lines that have actually been exercised and in red the lines that haven't been. And if you go and you look at this, what you'll see is that the majority of the lines that aren't covered are actually this error handling message. So in other words, with this test suite, what I'm doing is giving it perhaps reasonable physical input that I would normally have, but it's never giving me some weird input that puts me into a corner case where I've got this computed delta value that's 0, and I need to avoid that because that would give me this divide by 0 here. So that's to some degree a deficiency of my test suite. I might or might not accept that. I'm not putting in these exceptionally non-generic inputs that put me into a weird state. So code coverage is popular. gcov works for C and Fortran, and hopefully for whatever language you're using, you should be able to find a tool that should help you with this. And if you're anything like me, anytime I come across a new tool that I want to use, I'm going to try to study what is it that it actually does, what does it do well, what does it do for me, and specifically how should I not use it, or how should I be careful when I use it. So we can ask ourselves, what are the limitations of using code coverage by line? And Anshu already mentioned this a little bit. So let's imagine that I've written this particular function and I want to test it. We see it takes 2 parameters, P1 and P2, and then it has these 2 different branch blocks within it. And so this is my test suite over here. I've got test 1 and test 2. So test 1 is going to work with P1 is equal to A, P2 is equal to C, test 2 is going to work with P1 is equal to B, and P2 is equal to D. So when I run the code coverage on that test suite, I'm going to find that every single line in that block of code has been covered. It's been executed. But when we look at the combinatorics of this, we'll see that we have only actually executed 2 out of 4 pathways within this function. So in other words, if someone were to call P1A and P2D, there might actually be a bug there, right? We just don't know. So 100% code coverage does not necessarily mean no bugs. That's just something to be aware of. That doesn't mean that code coverage is bad or should be avoided. We just need to use it responsibly. So then we can ask ourselves, are there other types or other levels of code coverage? And we'll link this back to this morning. If we're doing test-driven development, what I'm fundamentally doing by writing the functionality and the test at the same time is I'm making sure that I'm covering my code in terms of functionality. Those tests that I created with test-driven development are definitely covering that functionality that they're paired with, right? And now the question is, does TDD mean, if I get all my tests passing, does that mean that everything's working as well? Is it bug-free? So I can give you an example of this. If we only use unit tests, that's the only place we're using TDD. So I only use it when I'm writing a function or a single class. Then what TDD is telling me that the functionality of those functions and those classes are working within that limited scope. However, when I try to tie that functionality, those functions and those classes together into larger functioning units, I don't have any tests there. So the interconnectivity of my functions and classes is not being particularly tested right now, right? So that might be something that we want to think of when we're doing test-driven development. Do we only want to just create classes at that lowest level? And so you guys were asking me a lot of very good questions about TDD, and I want to stop here for a moment and say, what happens actually if I did that case where I only have unit tests? So it seems like everything's wonderful, but then someone points out to me like 2 months later that I've got a bug. Did I fail in my TDD? I made this decision potentially to just to put it at the level of unit tests because that was reasonable for me. So how should I proceed with this? So what the TDD people would tell you is actually figure out why the bug is happening, but don't fix it yet. Write a test that's capable of catching that bug. Write it, run it, and see that it's failing, to go back to that red state. Now that you've got that test there, you've covered that gap in your code coverage by functionality, then fix the bug and see that your test goes back to green, right? And then finally, another level of code coverage is if we think back to the requirements and the verification, right? We're coming up with these requirements, this functionality, and this constraints, and we're at the same time designing some tests to make sure that we've satisfied that. So that is functioning as really code coverage at a higher level, right? And so it's going to depend, its effectiveness is going to depend on how well we've done the requirements in terms of completeness, for instance. So now we'll move back to continuous integration. And the short and sweet of continuous integration for me is this goal that's written here in bold. We want to have a master branch that always works, right? The fact that that phrase contains, or that sentence contains the phrase master branch tells us that continuous integration is fundamentally linked to version control, right? And hopefully this goal sounds very familiar to you based on what we were talking about with Git workflows, right? We want to collaborate well so that we can achieve that goal. So a good place to start with continuous integration is coming up with a good workflow that isolates the master from the integration environment, as we were doing in some of those examples. However, as you guys quickly sort of found out through your questioning, what we had done was a bit insufficient because we didn't build any particular rules or policies in that help us really address some of the difficulties associated with integration. So for instance, I haven't done anything to minimize the likelihood of merge conflicts, and why we built into that Flash 5 some notion of testing as part of the workflow. We could have done a better job so that when a bug is found or is injected into the code, into the repository, we can find it immediately so that we can debug it both quickly and easily. So the first rule that we're going to add on to our workflow is this rule that all developers must commit and integrate often. This is where the term continuous integration originally came with. I think nowadays we normally associate with continuous integration with the test servers that we're going to be running, and I'll talk about those. But this was the early days of it, committing and integrate often. The motivating factor for this is down here, and yet two more graphics that you guys have to suffer through. Another race condition. 2 developers on their long-lived feature branches. They're, let's say, a month long of effort, 12 commits. By the time this poor dev 2 loses out and tries to integrate their work into the master branch, the reality is that those two long-lived feature branches have probably diverged significantly. And so therefore, there's a higher likelihood of conflicts and a higher likelihood of committing bugs or creating bugs when we try to resolve those conflicts. So if we ask workers, the different developers, to commit and integrate often, what we're telling them is when you've got that massive job that's going to take you months to do, decompose it into smaller individual tasks. And each one of those tasks can be put onto its own individual feature branch. And that's what we see down here. We haven't gotten rid of the race conditions. But the idea is when I have two branches that are in this race condition, they're going to be short-lived. It's highly likely that there won't even be any merge conflicts between them. And in the unlikely case that there is, hopefully it won't be so bad to resolve. So it's going to be less risky, and it's going to be more enjoyable for us. We can try to decrease all that difficulty with integration. So the second level then is we want to come up with some policies or rules where we're going to start to insist that people test the code every time that they integrate the code in interesting places in the repository, right? What we want to do is control the quality, and we want to hopefully, if we couple this with that previous rule of commit and integrate often, what should happen is when this immediate testing does discover a bug, well, hopefully we're going to isolate to just a handful of commits on some short-lived feature branch, right? So that means I should be able to zero on it pretty quickly. And also, chances are that I've just been working on those broken commits in the recent past, so my brain's already sort of primed and it knows exactly what it was doing. So hopefully it should be pretty quick to actually fix it. Whereas if I was working with a very long feature branch that took a month to develop, the worst case, it was the first commit, and I'm going to have to do that context switching to load back into my brain what I was thinking about a month ago when I actually created that bug. So what we want then is a system that's going to trigger automated build and test cycles on our test environment, our target environments of choice, whenever the code changes in the repository in a significant way. And we would also like to do, if we have these merges, is that any time someone tries to issue a pull request to do a merge, that we want to have the test, this build test cycle run first on the proposed merge product before we actually finalize that merge. And so, of course, these beautiful systems exist. They're called build servers and test servers. We like them because there is this policy that we've built into the workflow, but they're going to actually automate it away from us, right? So it's going to be very easy to implement. It's going to be very easy to enforce. So they're a great solution, and they do everything that we expect them to do. Some examples of these are CTest, CDash, Jenkins, Travis CI, and GitLab CI. And so we'll concentrate on those last two, which could be classified as cloud-based test servers. So the idea is we've got our code in some nice version control host like GitHub, and we've got this nice build server that we would like to do, so we want to try to connect these two through a two-way communication. And so we have, for instance, GitHub. If you go to their web page, you'll see them mention Travis CI. GitLab will mention GitLab CI, and we have Bitbucket's pipelines. So the idea here would be that when someone makes a change in the code and they push that to the remote repository, we want that service like GitHub to communicate that fact to the test server, the build server, Travis CI in this particular example, and it will initiate that build test cycle. And the same thing with pull requests. And those build test cycles are being run in a containerized cloud system. When it's run its tests, it's going to collect that pass or fail status and transfer it back to GitHub so that GitHub can put that result next to commits and in pull requests and things like that so the developers can get their feedback. And what I want to point out at this point in time is that these build servers, they're just executing commands. They have no idea that they're actually executing tests. In fact, they don't have to execute tests. So we can be fairly creative about how we actually set up these services. So we can trigger that code coverage analysis, or we can have it also build documentation for us if we want to. So continuous integration has existed for some time, and interest is clearly growing. In fact, we have a part of the HPC community working with CI developers, or excuse me, providers, to help them adapt CI to the challenges of running on HPC machines and running HPC software. Of course, nothing is free in life, so you can't just click a button and expect CI to work magic for you. So there is some effort that you have to put in terms of setting it up. And I think more importantly, you have to both to maintain and monitor not just the CI but also your test suite. The reason that is important because eventually people, when they make a change in the repository, they want to know that CI is running. When they come back an hour later, just see that little green check mark indicating success. and they want to know that that's reliable. They want to see that green check mark and not doubt whether or not the CI was working well, not doubt whether or not the testing suite was working. They just want to move on to the next task. So it's important, I think, for people to have that confidence in that single result. Some prerequisites that need to be satisfied for CI is that we need an automated build system. We need an automated testing system. We want to hopefully have significant test coverage. And importantly, we need that testing framework to feed back that pass and fail status in a way that's compatible with what that test server needs. And we'll see that again as we go through this example. And as Anshu pointed out, if you're using, for instance, the public version of Travis CI, oftentimes they give you a restricted amount of time in which you can run your build and test cycle. I think it's about 50 minutes. So if your test suite is going to run for far more than 50 minutes, it might be in your benefit to come up with a way to structure your test suite so that you can bundle up a certain subset of tests in that test suite. So this month we're going to be working on just this particular functionality of the code. There's 5 tests that I need to run that covers that functionality, so I'm going to pop that into my test server. And then the next month when we're working on a different part of the functionality, I pop that out and I pop in this 10 set of tests that cover that new functionality. It would be very nice to have that level of flexibility. So now what we can do is transition over to GitHub and to Travis, where I've created these very simplistic repositories. What they're going to do is, to the best of my knowledge, this is my form of doing a hello world of continuous integration. So the minimal content that I need to have in a repository so that we can hook it up to Travis CI and see that little green check mark that we all like so much. So can people read that? Is that big enough? Yeah? In the back? Thumbs up? Thumbs up. OK, we're good. So what we see here when we go to this repository is that there's only 3 files here, and the README doesn't count. We've got that .travis.yaml file. That's the configuration file that we need to put in the repository so that we can hook up GitHub and Travis CI, and so the Travis CI knows what it needs to do during that build and test cycle. And down here we've got this little script here called hello world.sh. That's a bash script that's just filling the role of a test suite to make sure that we've configured everything properly. And so if we drill down now into travis.yaml, what we'll see is that this file is structured into blocks. And Travis CI will walk through these blocks in a particular order and execute them for us. At the top, what we put in is particular information, like so language and what platform we want to run on. And that's going to help Travis CI decide what default environment it should give us so that we can run this build and test cycle. The next one down is env. And what we're doing here is setting an environment variable called Travis CI env to the phrase hello world. Once that phase is finished, then Travis CI would move on to the before install. And these are typically where we would run commands to help augment that default build environment that we were given. So for instance, if I need some library or tool that isn't already in that build environment, I can either get it or build it in this step. And what I want to point out is you see that this can actually, each phase can contain multiple lines. And so Travis CI is going to run that command. The way it's going to determine whether or not that command was successful, it's going to run it and it's going to collect the error code. If the error code is 0, it's going to interpret that as a success. If the error code was 1, it's going to interpret it as a failure, and it's going to abort in this particular case and say that the build failed. But let's say it goes all the way through, and then it would go up to the install phase. And here what it would do, typically what we would do is this is where we would build our test suites that we want to run. Right? Same idea. And then we go down to the before script phase. And so what we're doing here is we're actually printing out the contents of that environment variable. This is what we're trying to achieve, people. We're trying to see in the nice Travis CI log the phrase hello world so that our lives will all be complete. And once it does that, then it would move on to the script phase. And this is typically where you would actually run your test suites. So in this case, we're going to be running that hello world script. Right? So there are some subtle differences. So in the install phase, for instance, if any single command fails, then Travis CI is just going to abort there. It's not going to proceed on through the rest of the phase. Whereas with the script, it's going to run every single command in there, regardless of how a previous command exited. Okay? And then based on the success or failure of that script block, Travis CI will either run after success or after failure. So we're going to print out more useful information in the log file. And then there are, of course, other phases that Travis CI can use. And I've put one example here in the form of after script. So this is where you can clean up. This is where if you want to trigger code coverage analysis, you can do it there. If you want to build your documentation, that's a place where you could always also go as well. So our test suite is this little script here. The first thing it's going to do is confirm that, or check if that environment variable exists. If it doesn't, it's going to print a helpful error message. If it does, and it would return with an exit code of 1, which should be interpreted as failure. If it exists but it doesn't have the right content, then it's going to report a different message, and it's going to terminate with an error code of 2, which would again be interpreted as failure. If everything runs through to the end, then by default it will return that error code of 0, which should be interpreted as success. So now what we can do is go look at the commit history, and we'll see that the first step, all I did was put in that README file. So there's no test suite, there's no Travis configuration file, so I can't connect them, and I can't expect any test suite to get run. The second commit, I put in now the test script, same situation. And not surprisingly, that in the third, I now have that .travis.yaml file, which is critical. At this point, I can connect those two repositories and expect to get some result. And what I'll point out up front is that I've got the environment variable lines commented out. So we should get a failure with that exit code 1. And when we look here, what we see is that indeed we get that nice red X. Travis CI is telling me that things failed. And if we click over, we can see the actual log for that. And so what we see is, for instance, there, Travis CI is cloning my repository. And if we come down here, we're now at that before script phase, part of the Travis CI. And we see that it tried to print it, got nothing. The test script failed, and it returned that error code of 1. We see that Travis CI interpreted that as a failure. We know that because it ran the after failure bubble, right? So then the next commit, I tried to do a better job. So here I uncommented that, but I still don't have the right content, of course. We're still getting a red X. And if we click over, we should see an error code of 2, still being interpreted as failure. So we're still on the right track. And then finally, I did what I was supposed to do. It's being set to hello world. We got that lovely green check mark. And when I come across, we see that indeed, at that before script phase, we're seeing we're seeing hello world printed out, error code of 0, and we ran the after success part with Travis CI. So now everything has functioned properly. So if we have time, what I can do, I have another account here. We can actually try to break it and see if we can get Travis CI doing some work for us. So I'll fork it. And at this point, I should be able to go over to my Travis CI and synchronize. And there it found that repository, and I can click it on. So now I've established that two-way communication. And what we'll do is we'll update our expectations in the error, in the test suite. So we'll put on an exclamation point, put something there, and we'll commit it. And now if we come back and we look at the commit history, we've got 6 commits. We've got that little orange bubble, which is Travis CI telling us that it's busy. And then we can watch it churn a little bit. So it's booting that container. It'll actually pull down the repository at some point. It's setting up that build environment, right? So I can also point out while it's doing that, you have like helpful information here. So if you want to see what were the actual changes you made, you can click over and you can see that it was just that exclamation mark. And we're running this on a Linux target at the moment. The default environment that it gave me was Ruby, and then it's telling me about my environment variable. So at this point, we might be in a bad state. This happened to me the other day when I was trying this out. So Travis CI just appears to be busy at the moment. So when I did this other times, it would generally run about 45 seconds, I would think. So we're there right now. Does anyone have any questions while this is running? On code coverage or CI? Yes?
So part of high performance computing is running on these like crazy architectures that are really heterogeneous.
Excuse me?
So part of what we're sort of working on is running on these architectures that are pretty heterogeneous.
Yep.
does Travis have the ability to run, say, on a GPU or?
So like right now, for instance, we're running on, because this is public Travis CI, we're running on some servers associated with Travis CI, so we're a little bit limited. I think you can choose, there are certain things that you can do to choose between different ones. So I could choose to run on Mac OS, and I think I could choose to run it on different servers that I know have different hardware. So the ECP, the Exascale Computing Project, they're working together with, I believe, is it GitLab CI? GitLab CI, and they're trying to get them to update that product so that it can run on DOE machines, for instance, and that people can run it on those particular machines. So that's, it's in progress. I believe that there are people beta testing it at the moment. Is that right? Yeah. And so there you would be able to do that sort of
And
mission.
that sort of resource would be accessible to anybody, or just the people that have like the huge allocations?
I don't know the answer to that. Do you know, Jim?
I don't think it's necessarily going to be either of those extremes, and the extent to which there will be, big allocations for long run times is certainly very much up in the air. The initial push is going to be for compilation and for small scale. There's some questions that we could talk about later.
So this is a follow-up for the guys. So if I were to let's say as a CUDA code, so I cannot, if I understood correctly, if I wanted to do a CI on my CUDA code, then based on the current CI capability, I cannot pick a GPU from the back.
Off the top of my head, I really don't know if they have GPUs on these servers. I would be a bit surprised. So yeah, you would have to link up this sort of facility with a machine that actually has that. So with Flash, for instance, we're not using Travis CI yet. We actually have we use Jenkins to trigger our tests, and those are running on particular machines that we have access to at Argonne. So we can use those to run on those particular
machines. You
machines.
can configure the different CIs on your local machines, as long as the software is specific.
So I don't know too much about configuration, but the idea would be look to see if you can find other providers that have this framework that allow you to do this automation essentially, right? On the machines that you actually need to test on. Yeah. Yep.
Okay, I'm sorry if you said that already, but so the only thing that you need is this YAML file to be present, and it's going to run the test for you. You don't have to set anything in your Git.
Yeah, well, you need to connect it like I did, and then you need to have that configuration file set up correctly and running. So there are some challenges with that, because if you do this the simple way and you try to write your .travis.yaml file and you try to put in a single test, you have to go and trigger a change in the code and then wait for Travis CI to run and then see what the result is and then find out that you left out a semicolon and try again. But I have a coworker at Argonne who told me that he's found a solution where he's been able to run Travis CI locally in I think a container on his own machine. And when he's been able to do that, that has been made the process of getting .travis.yaml file working correctly. Unfortunately, I don't know the details of that yet. But so for the hello world, we didn't do too bad, right? 2 files, not a tremendous amount of work. And it seems like we might have our solution coming out now. So there we get the hello world, which is not correct, and we get the error code of 2. So normally I would go back and fix the configuration script, put in the exclamation mark, and see it go green, which is, of course, what we're all living for. But I think we can skip that, right? We're already at 4 o'clock. I don't want to take any more of Anshu's time. So thank you all very much.